Okay, well still, let's look at some more. Here's number 4. And it's essentially the same idea as the previous example 3, just in a more general situation. So you could choose some basis of your space X, and it's actually not too important here whether the enumeration is over the integers or over the natural numbers. And then, just like in example 3, you do your truncations on the level of the coefficients for your basis elements. So you take the expansion of your arbitrary element from X with respect to that basis here and truncate it. This reminds me that we should say a few more words on the word basis in infinite dimensional spaces. So let's start with a family B of elements from our space X, and let's say that the span of that family B is the set of all finite linear combinations of elements bk from our family B. Okay, finite is important here, so no limits so far. And then you say that this family B, well, provided it is linearly independent, is called a Hamel basis of your space X if X equals the span of B. And you call it a Schauder basis. I was using that word a bit earlier already. If this equality holds after taking the closure. So if you have a Hamel basis, then every element of your space X can be written as a finite linear combination of little b's. Whereas if you have a Schauder basis, then every element of X can be approximated by finite linear combinations of little b's from B. So here we are talking about infinite sums, which means limits of sequences of finite sums. So when we say basis here, we clearly mean Schauder basis. And the same is true in the previous example with the Fourier expansions. To practice this basis stuff a little bit, let me give you a little exercise. In our sequence spaces, we sometimes speak of the standard basis, where the first basis element is the sequence that has 1 at the first position and zeros everywhere else. The second basis element has 1 at the second position and 0 everywhere else, and so on. So is that what we call the standard basis? A Schauder basis or a Hamel basis of your space X? Well, I have to give you X. And actually, let me give you 2 spaces X. Let me give you X equal to C0 and also X equal to C00. 0. Okay, and you should answer both. So the answer might be different for this and that. Good, so that was our insert on Schauder and Hamel basis. Our fifth example is a particular instance of example number 4. If we have L2 on the positive half line, then we can write down explicitly an orthonormal basis where the kth element is given by e to the minus t half times the kth Laguerre polynomial at point t. And the Laguerre polynomials are polynomials in t, and they are orthogonal to each other, and they are exactly what you get when you apply Gram-Schmidt orthonormalization to the sequence of monomials in T. I'm sure you remember that exercise from your first year linear algebra course. Okay, and Lk is a polynomial of order k, so there's something to do with t to the power of k. So you know that when t goes to infinity, this will go to infinity, and quite heavily if k is large. And for this to be a function in L2, you need this decay towards infinity. So this here is essentially a damping factor that brings your polynomial growth down to 0, because, well, we know that exponentials go to infinity even stronger than, or even faster than polynomials, and note the minus sign in front here, so you divide by an exponential. Okay, and then you define your projections Pn by the same procedure as you did here in number 4. And I mean, in all these truncation examples, number 3, the Fourier coefficients, and then 4 and 5, it's fairly clear that Pn is a projection, because if you apply this truncation procedure here again to the result, so if you tell it to reduce summation to the first n terms, then of course it will not change anymore. You're already at the result. And the other question is about the strong convergence to the identity operator. So what happens if you move n out to infinity? Well, then by definition of that series, you have convergence as n goes to infinity, and you have convergence to the thing that is here on the left. This is exactly how you define this notation here of a series. So this is all clear here, that you get projections and you get strong convergence to identity. Example 6 is a simple extension of example 5. So while in example 5 we were talking about functions on the positive half axis, we're now talking about functions on the whole axis. But let's just split that in the positive and the negative half axis and then treat each one of them as we did in example 5. Okay, so you get one basis for the left half axis and one basis for the right half axis, and because these are connected by a direct sum, you could just join these bases into a basis of your whole space X here. Well, let's say one is enumerated over the natural numbers, the other one is enumerated over the negatives of the natural numbers, and if you join them, then you have a basis that's enumerated over the integers. But now it remains to use the same truncation idea that we had here in this general technique, example 4, but only you have to truncate at both ends. And again, it's clear that if you repeat that process, you don't change the result anymore, and that if you move n out to infinity, then you get convergence to the original element.